Okay, for our next segment, we're going to look at energy conservation. Um, so let's click back into Logger Pro. We're still using clip 14. Um, and for this segment, we're going to do all our calculations on this Word document, which you can see here to the right. Now, there are two forms of energy that we can analyze here. We can analyze the kinetic energy of the ball, the energy of motion, and the potential energy of the ball, the energy the ball has relative to its height above the ground. The ball's initial energy is the energy it has the moment it's released from my hand, and the ball's final energy is the moment just before it enters the rim. So these times, the initial energy was taken at a time of 2.203 seconds here, and the ball's final final energy was taken at time 3.370 seconds. So now let's go ahead and look at our calculations. Okay, so we know that kinetic energy, the equation for kinetic energy is 1/2 mass of the object times the velocity at a certain time squared. And the potential energy of the object, cancel that, is the object's mass times gravity times height. Notice how there's two m's and there's an m in both equations. We can ignore the object's mass. So therefore, kinetic energy is essentially the 1/2 times the velocity squared, and potential energy is essentially gravity times the object's height off the ground. So in our data table, we're first going to look at the initial kinetic energy at time 2.203. So that is here. Let's go ahead and highlight it. All right. Now, we are given a y velocity and an x velocity, but we don't want them in components. We want the vector sum of velocity. So to get that, we use the Pythagorean theorem, which states that unit a squared plus unit b squared equals a combined unit c squared. So essentially, we square the y velocity, we square the x velocity, we add them together, and then we take the square root of that, which yields the common velocity vector. Doing this for time 2.203 seconds. Oh, and for all x velocities, I used the average value for velocity as determined previously in the experiment, which was negative 3.152 meters per second. So using these values, our initial kinetic energy was 21.545 joules. Furthermore, in looking at our potential energy at 2.203 seconds, we see that we are at a height of 2.747 meters above the ground, which yields a potential energy of 26.921 joules. Now, for our final kinetic energy, that takes place at time 3.370 seconds, as highlighted to the left here. Once again, we use the Pythagorean theorem to determine our velocity, and it comes out to be 5.597 meters per second. We square that and multiply by 0.5, and that yields 16.555 joules of energy in the kinetic form. And then we notice that our height at time 3.370 seconds is 3.044 meters above the ground, which yields a potential energy of 29.831 joules. Now, looking at initial and final energy of the system, the ball system, we add kinetic and potential energy together. The initial kinetic and potential energy we add, and then we add the final kinetic and potential energy. So the total initial energy is 48.465 joules, and the total final energy is 46.386 joules. And the percent difference between these two values is 4.384%, as indicated right here. Now, in terms of energy conservation, these values should be, if this experiment were conducted in a vacuum, these values should be um, exactly the same. However, due to air resistance and slight inaccuracies in the plotting of points, there was, a little bit of error. And in my approximation, that error should have been around 5%. And our percent error for this experiment of 4.384% falls within that range. Therefore, I feel comfortable saying that the energy of the system was conserved.